Okay, this problem, also an electrostatic problem, where we use Gauss's law to compute the electric field in a coax cylinder like this. So what do we have? Let me magnify this. All right, so we have a solid cylinder in the center. This is solid. Let's see. Non-conductor has a density ρ2 and radius r1. Then there's like an air gap or vacuum. And then there's a cylindrical shell of inner radius r2 and outer radius r3 that has a different charge density. I mean, it could be the same, okay? And we want to compute the electric field using Gauss's law in this region right here, inside the inner cylinder, between the cylinder and the shell, inside the shell, somewhere here, and then outside the shell, okay? Now, this all hinges on ρ1 and ρ2. So we're going to consider two scenarios where ρ1 probably is constant and ρ2 depends on the radial distance, or vice versa. It doesn't really matter, okay? So whenever we're doing Gauss's law, we start off with this equation like this. And we need to get a symmetric surface surrounding our charge distribution so that we can do this integral on the left right here. This integral on the left is extremely important, but for all intents and purposes, we only have two answers for this. One answer when we have a sphere and one answer when we have a cylinder. It always works out the same. Again, because we're dealing with simple problems with spherical or cylindrical symmetry. Now, if the problem was more complicated and Gauss's surface, the Gaussian surface we choose is neither, then we have to really work on this integral. But so what's the challenge? The challenge is Q enclosed. This is what it comes down to, is can you find Q enclosed inside, this Gaussian surface? That's what Q enclosed is, okay? Now, since we're dealing with a cylinder, it is good to know that the cylindrical volume element is given by this. dV is R, which is the radial distance from the axis of the cylinder. dr d theta or d phi goes around the cylinder, and then z is the length, goes along the length of the cylinder, okay? So before we decide what ρ1 and ρ2 are, or just take examples with ρ1 and ρ2, let's go ahead and do this equation as if we know what Q enclosed is. And then our job is to compute Q enclosed in these three regions, for 1, 2, 3, 4 regions, based on ρ1 and ρ2. All right. So how do we do it? For all these cases, we choose a Gaussian surface, okay, in the shape of a cylinder of length, say L. Okay, so whether we are inside the solid one right here, or surrounding it, or we're inside the shell or outside it, our Gaussian surface will always be a cylinder of length L and radius little r, which is our variable. So then what will we have? So we have, if we have a cylinder, radius r and length L, okay, we have, and because of the cylindrical symmetry here, and again, rho is going to only have radial component. The density, we're only going to take it to have radial component, no angular component, and no z component, okay? Just radial. So this cylinder is composed of 3 areas, right? Okay? This cylinder has 3 areas, surface areas. One is the side, 2 are the caps. Two caps we have, 3 areas. Okay? So this integral on the left breaks up into integral of the side of E dot dA plus integral cap 1 or left cap L cap E dot dA plus integral of the right cap E dot dA. We're still working on the left integral. For the sphere, will be easy. It's just one sphere, right? There's no caps or anything like that for a sphere. Now let's look at the first cap, the second cap, and then the surface, which we'll now draw in a different color. Maybe I'll use here. And this is the electric field. Okay. Now the area vector, remember area is a vector. It's perpendicular to the surface, pointing out from the inside volume. And on the surface of the cylinder, the A will look like this. This is E. So on the caps, here's E, here's E. Okay. Now again, what is E dot dA? E dot dA is basically the flux, well, on the side, it's the flux, the electric flux going through the side of the cylinder. And on the left cap, E dot dA is the flux going through the left side. And then the right cap is the flux, this integral here is the flux through the right cap. Now, forget about the dot product. If we just look at the caps, we see the electric field is, on this page, is vertical. The area is to the left. And we just have a cap, right? Forget about the area also. Just the electric field going up, straight up. How much electric field goes through the surface of the cap? Okay. Again, this is an infinitesimally small cap, and the electric fields are just imaginary lines going through. Hardly any. No electric field would go through the cap. Okay. Mathematically, E is vertical, dA is horizontal, the dot product is 0. Okay. Just from the physical fact that, again, if E is totally vertical, there is no component of E going through that surface. Okay. So we'll just go, there's no flux going through that surface. So now, we can simplify that integral. So here we could say that's 0, and that's 0. Okay. And again, that's now again, this is an imaginary surface, the caps. You could think of them as also whatever E enters through the cap, E leaves through the cap also. So there's no net flux. There are many ways to interpret it physically, but mathematically it's pretty straightforward. Oops. is integral on the side of E dot dA, and this one goes integral the side E dA. The dot product changes into a regular product. But E is constant on the surface. Therefore, integral of EdA on the surface is just E integral dA of the surface. So whenever I integrate the surface of a cylinder of length L, again, the length here is L, and the radius is R, I get the circumference times the length, the circumference of that circle times the length. So that will be E times 2 pi R L, right? So this is the integral on the left. And always, 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 now, unless we're talking about an infinite sheet, the contribution of the caps, whenever we have a cylindrical object, usually the caps don't contribute. Okay, only the side of the cylinder, the Gaussian surface, right? The Gaussian surface will only have the sides contribute to it. Okay, the caps don't contribute anything. There's no net flux going through the caps. All right, so now E dot dl, E times 2 pi r L is Q enclosed over epsilon naught. And then so E, remember E is radial, so we're not going to put the vector here, just put, once we get it, we'll say it's radial. It's, yeah, Q enclosed over 2 pi r L epsilon naught. Okay. So now my job is to compute Q enclosed for every situation. So first, let's assume the first situation, put maybe 1 here. Assume that rho 1 equals rho 2 equals some constant charge density. We can make them different, right? But nonetheless constant. Equals, constant. Right? Like coulombs, per meter cube or something. Some kind of number. Right? So now, what is the electric field in each of the regions? Right? So when I'm inside, so basically part A, I'm inside the cylinder. Okay. Here's my cylinder of radius R1, capital R1. And my Gaussian surface, I take it a cylinder of little radius R, length L, inside it. So little r is smaller than capital R. So this equation telling me is asking me to compute the Q enclosed in this white surface here, in this Gaussian surface. But if rho here inside this cylinder is constant, then the amount of charge is just the density times the volume of this Gaussian cylinder, right? This is how you compute, for example, mass. Mass is density times volume, but here you're assuming density is uniform. So whatever volume you have, you multiply the density with the, by that, and you get the mass. Same thing here. The charge enclosed in this white part right here is just the Q enclosed Again, our cylinder, have to remember, the Gaussian surface has radius r, length L. For all of these problems, our Gaussian surface has a little radius r, length L. Here, little r is less than capital R1. So Q enclosed is basically rho 0 times the volume, the Gaussian volume. Well, I have a cylinder, right? What's the volume of a cylinder? It's the area of the cap times the length. So now that I know what Q enclosed is, E equals Q enclosed rho 0 pi r squared L over 2 pi RL epsilon 0. Pi cancels, one of the R cancels, the L cancels. L should not enter into this, right? So this will be rho 0 R over 2 epsilon 0. Okay? And that's the electric field for R less than R1. Part A. Now for part B, between the cylinders. In other words, I am between R1 and R2. So little r now is between R1 and R2. So R, R1, R2. Okay? So what do we have here? Again, let me just make a little drawing. This is my R1. That's my inside cylinder, the solid cylinder. Here's my Gaussian surface. I take it at a radius R, bigger than R1, but less than R2, and a length L. Again, all my Gaussian surfaces for this problem, radius R, length L. So again, I ask myself, how much charge is enclosed inside this white surface? Well, it's the whole inner cylinder. And there's nothing else. I mean, there's nothing between the edge of the inner cylinder and the edge of the Gaussian surface. So it's just the inner cylinder. So Q enclosed, again, is Q, on the, or, oops. Okay, where did it go? Q inside the Gaussian cylinder. Q cylinder. What is that equal to? If I have all my inside cylinder, I want to take into account for that. Again, the Q is the density times the volume of the cylinder. Okay? It's the volume of the cylinder. Now the Gauss, again, this cylinder of R1. Well, rho 0, the volume is the area of the cap times the length. So now E is Q enclosed, rho 0, pi R1 squared L over 2 pi RL epsilon 0. L cancels out, pi cancels out, rho R1 squared, L goes away, over 2 R epsilon 0. That's between the cylinders, and that's what R is less than R1, I mean, it's greater than R1, but less than R2. And in a way, this makes sense. When we're inside, okay, the electric field is going to increase as we go away from the center because we're accumulating more charge inside our Gaussian surface, or inside our radius, if you may, while we're inside the cylinder R1. That was part A. So as we go out, the electric field increases, and in this case, it increases linearly because rho is constant. When we are outside the cylinder, we don't know that there's a shell right above us, right? We're just outside the cylinder. So the farther away we go from that cylinder, the electric field will appear smaller and smaller. So this one diminishes as 1 over r. In other words, inverse of the radial distance, which makes sense. Whether it's correct, is it 1 over r squared? Is it 1 over r? 1 over r cubed? That will have to go with the math and, depending on the density and all of those. But we are outside the cylinder, and the electric field must diminish because we are not accumulating any more charge as we go farther away from the cylinder. Now, in this case, we're going to run into the shell. Okay, so that's part C. Inside the shell, that's when R is between R2 and R3. So here is my, let's see if I can get this straight. I'm just drawing here's the center of the cylinder. Here is R1 inside. This is the solid cylinder. This is R2. This is R3. I'm inside the shell. My Gaussian surface lives inside the shell, a distance R. Right? So now, how much charge is inside this Gaussian surface, that cylinder of radius r and length L? Again, that's a cross-section image of it. Well, obviously, I have all the charge from the inner cylinder right here, plus whatever amount of charge here I'm going to accumulate. Okay? So now, the question is, how much charge is here? Because we already know how much charge in here. It's this. It's this. Because again, I'm encircling all of the inner cylinder. Okay, I'm encircling all of the inner cylinder. So this is how much charge is inside, but then there is this much charge right here. So basically, Q enclosed is Q in the shell, the only part in the shell that's enclosed, right? Not the whole shell, plus the Q in the cylinder, part or partial. Well, we already know what the Q of the cylinder is. This one is rho 0 pi R1 squared times L. But how about here? Well, again, we need this volume right here. How to get this volume of this little shell right there? Well, you could imagine the white cylinder, okay, of length L, or a white cylinder of length L, and then take away, of radius R, and then take away another cylinder inside it along its axis of radius R2. Okay, so it's like a cylinder, and you drill a hole in it, and you grab that hole and then subtract it off. That's what it is. Okay. So again, imagine the Gaussian surface to be a cylinder of, again, of radius r of length L. And then to account for this much charge, we need the volume of this. So you take that cylinder of radius r, and then you take away this cylinder, and you're left with the shell. So the shell will be Q of cylinder of radius r, this is at r, minus, well, let's volume, it's better. It's rho 0 times the volume at radius r minus the volume at radius R2. Okay? That is the volume of that little shell of the white lines right there. Okay? Just like, let's just take a simple example just to make it clear. Here's a circle, there's a cylinder, and I have a hole inside the circle. What's the area right in here? If the hole has a radius A, the circle has a radius B. Well, you could think of, get the area of the circle of radius B, take away another circle of radius A. And that's the area right here. Okay? So it's a circle of B minus another circle of radius A. And that will give you that shaded stuff. Same thing here. The volume of the big cylinder, take away a bored cylinder inside of radius R2, and that is your volume of that shell, that little shell, times the density will give me the charge in that shell, plus the charge from the inner cylinder. So what's the volume at radius R? Again, is pi r squared times L minus the volume at radius 2 plus rho 0 pi r1 squared L. So let's factor pi L from this rho 0. So it's rho 0 pi L. What do I have here? I have r squared minus r2 squared plus r1 squared. This is the charge enclosed inside that Gaussian surface, the white Gaussian surface right there. So now the electric field is Q enclosed over 2 pi, what was it? Keep forgetting, 2 pi RL epsilon 0. Pi L cancel out, and I'm left with rho r squared plus r1 squared minus r2 squared over 2 r epsilon naught. Okay. And there it is. And this is, again, my little r is between R2 and R3. Now let me go outside. So part D. When R is greater than R3, what do we have? Again, cross section, R1, R2, R3. My Gaussian surface has to contain, has a distance R outside R3. So my Gaussian surface contains the shell and contains the inner cylinder. So Q, now it's Q shell total plus Q cylinder total. Okay? And Q shell now has the same approach as the Q of this little thin shell right here. But now I'm considering the whole shell, not portion of it. So this will be rho 0, the volume at R3, the big volume, take away the volume at R2, plus, this is rho 0 pi R1 squared L. Here's rho 0. The volume at R3 is going to be pi R3 squared L. Volume at R2 is pi R2 squared L plus rho 0 pi R1 squared L. So take out L pi rho 0. I have R3 cubed plus, squared, R1 squared minus R2 squared. Therefore, the electric field, Q enclosed, two pi R L epsilon naught. The pi L cancels. So I have rho 0. These are constants. We have fixed radii for the, and again, pi L goes away. The electric field outside, this is for R greater than R3, goes as 1 over R, because as we make our Gaussian surface bigger and bigger, in other words, as we move farther away from this coax, okay, the electric field is going to diminish because there's, a limited amount of, there's only so much charge on there, right? Remember, the caps do not contribute. So yeah, as we go out some more, the electric field is going to diminish as 1 over R. So we get to infinity, and then it's probably the electric field is 0. Okay. Or probably approach, yeah, it will go to 0 as R goes to infinity. And this is it. Now, in the next video, I'm going to begin from here, take it from, using the same document. And however, now, instead of rho 1, rho 2, rho 0, equal rho 0, which is a constant, I want to make them a function of the radius. So I'll probably make rho 1 a function of R, or of R squared, and rho 2 a function of R, or vice versa. And then see how we can compute the electric field in these 4 regions. All right? So that will be in the next video for the coax cylinder. I hope this has been helpful. Let me know if you have any questions.